are going to move on to the second part of our presentations today. We have a presentation on atmospheric radiation. In the book itself, in the Lectures in Climate Change book, this was a contribution by Valdar Oinas. And today we are going to have this contribution shared by Andy Lasis. So we are going to get started up here. I think if everybody can see this okay, we're going to turn it over to Andy to give a bit of an introduction. David, to give a bit of an introduction.
So Valdar could not be here, but I'll just give a brief introduction to him. He's the senior research scientist at GISS. He's now fully retired. He taught physics at CUNY Queensborough College in New York and has been a member of the GISS climate modeling group since the mid-1970s. His chief area of expertise is the development of fast and accurate radiative transfer techniques for modeling solar and thermal radiation in the study of global climate change, and it has applications also to remote sensing. He's been a key developer of the GISS-GCM radiation modeling methodology. And of course, there's nobody better to give this presentation than the person who worked very closely with Valdar all these years, the head of the GISS radiation modeling effort, Andy Lasis, who actually had given a talk earlier in the series. Andy, thank you.
Thanks, David. Yeah, I'm filling in for Valdar, who wasn't able to be here today. But we have worked together for many years here, so I think I should be able to address most of the issues covered in this presentation.
And sorry, I'm just orienting some of these pictures. They got reoriented in the transfer.
Okay, yeah, the radiation is probably the most important physics process in the climate system. It covers a full range of complexity from kind of broad brush to very complicated and detailed stuff in there. So you have a choice of looking at either the whole forest or the trees or the branches or twigs and leaves and etc. in there. So let's start here with the solar radiation. The sun is the source of all the energy that drives the whole solar system. And as you can see, sunshine comes in a whole bunch of different wavelengths. And depending on the wavelength, some of that radiation, blue and the ultraviolet, gets reflected out to space. Some of it gets absorbed within the atmosphere, and most of it gets absorbed at the ground and the ocean surface. So roughly about 30% of the radiation gets reflected back to space, mostly by clouds, the ground surface, and then Rayleigh scattering and aerosols do some of the other fill in. On the absorption, water vapor is the main absorbing gas in the atmosphere. There about 20% of the radiation gets absorbed in the atmosphere, most of it by water vapor. And then second comes ozone, does an absorption. And then there are other things like aerosols, and clouds absorb some, and some trace gases. And a good half of the radiation gets absorbed at the ground surface and by the ocean. We have a similar situation for thermal radiation. And there on the left figure, we see the red curve is the heat or energy that gets emitted by the ground surface. And the blue is what gets transported out the atmosphere. So and the green part then is what's called the greenhouse effect. It's atmosphere absorbing the radiation and trapping it. The pie chart on the right shows again that water vapor is responsible for about half of the greenhouse effect. Clouds, or absorption by clouds in the long wave thermal radiation, contributes about 25%. And then carbon dioxide covers about 20%, and other small trace gases like methane, N2O, fluorocarbons. They cover a few percent in there. And the important aspect of this is that water vapor and clouds are what we call feedback processes, meaning that water vapor and clouds are dependent on the temperature, and it's a temperature that determines how much water vapor and clouds are in the atmosphere. Carbon dioxide, on the other hand, is once you put it into the atmosphere, it basically stays there for decades or even or much longer. In there, it gets recycled in the carbon cycle, but once you put the carbon molecules into the atmosphere, they stay there and do their radiative heating. And that's what's driving the global warming that we have going on these days. Now, here's where we get into some of the more detailed stuff. Clouds and aerosols are made up of, well, like water and some other substances like that. And we have to calculate how radiation interacts with them. Fortunately, there is a theoretical basis called Mie-Scattering, which can calculate exactly what happens to radiation that's incident on a, say, a cloud droplet or particle. But as you can see on the left part, when you change the size of the particle, the amount of reflection that it comes off of it is highly variable. So this is where radiation gets complicated, and we have to, we're fortunate to have the calculations that are able to do that, but then we have to kind of average over the particle sizes to get the kind of a more reasonable number that we can relate to in calculating the effects of clouds and aerosols. So on the right-hand side, for example, is the relative, well, it's called spectral extinction, or the effect of the scattering that the particles do. So you're probably familiar with the blue sky, which is called Rayleigh scattering. That's very, very small, tiny particles. That's the sharpest curve that you have there for particles that are essentially zero in radius. And as you increase the size, the spectral dependence becomes flatter until for large aerosol particles or cloud droplets, the spectral response is flat, and that's why clouds are white, and the sharp curve that you see there for the small particles like blue Rayleigh scattering, those are blue. And so very tiny aerosol particles are also going to be sort of bluish in color. And as you get bigger particles, they become more spectrally independent and white. So we have to take all this into account when we're doing calculations for climate modeling. So all of that depends on what's called the refractive index of the material. So I think we're familiar with water. Has a refractive index of 1.33, and that bends the light when you're at the interface. So actually, the refractive index is a function of wavelength. And so on the left part, you see the darker curve for water vapor, for liquid water. It has kind of curves down, and then the middle part in the near infrared, it has more fluctuations and then undergo. And on the far right, in the thermal radiation, it has further changes in the refractive index. That's a real part on the top. On the bottom is what's called the imaginary part of the refractive index. This is a measure of how much absorption that material will do. And so that one you see also is highly variable as a function of wavelength. And also what's illustrated in this figure is on the top that you can sort of see the curve. That's for ammonium sulfate, this aerosol particles in there. And some of those particles are subject to relative humidity changes. They pick up water vapor, and so they'll, change between the top curve and the water vapor. So if you have a very humid atmosphere, the particles soak up so much water that they become essentially cloud droplets and become essentially pure water. And so we have to model the refractive index change that takes place as the relative humidity changes. And you can see that it's a function of wavelength that we have to also take care of. And here is kind of a description of this Mie-Scattering. On the top is the skew is a kind of the fraction or the scattering efficiency. So Mie-Scattering is something that the particles can either scatter, bigger than their geometric size or smaller. And so the numbers there, one is would be the size of the geometric extinction or shadow of that particle, and the light impinging on it, the particle actually acts like it's twice as big as its size. And it has also, again, that wavelength dependence, and that's because of the relative humidity changes. So if we model the effects of aerosols in the climate model, then we have to do all this spectral integration in there. The middle curve is the what's called the single scattering albedo, the omega. It tells you what fraction of the incident light is going to be absorbed. So most of these, like water and aerosols, have a single scattering albedo that's like a unity or close to 1 in the visible wavelengths. By the way, the wavelength scale, that's a logarithmic scale from 1 to 100 microns. So it's visible in the left, and the infrared and thermal radiation on the going toward the right. So they're basically non-absorbing in the visible, and then they have strong absorption features in the infrared. And the bottom rows is this symmetry parameter that tells you how much of the scattering is in the forward direction or side directions. So, and this is again maybe a more direct example of what happens in the spectrum dependence, and when you're looking at the see on the left, the red is the solar radiation, incident solar radiation in the UV part of the spectrum. It's got a lot of variability in it. The green part is a cloud, a water cloud that does a lot of reflecting. The right-hand side on that figure, the y-axis, gives you the fraction of light that gets reflected. And the blue in the middle is kind of a clear sky kind of a dependence on the radiation. And then the bottom curve, the black one, is desert dust. That is more absorbing. So those are, again, things that we have to take into account. On the right is a kind of example of a cloud dependence on the reflectivity in the near infrared. It depends on the composition, whether it's water or ice, or also on the particle size. So, okay, here we have another couple figures that got flipped. These are the cloud albedo, or the reflectivity of the cloud that we're calculating as a function of everything that's in the model. And this is shown as a function of the solar zenith angle, or the sun angle. So cosine of 1 means the sun overhead, and on the left is the sun on the horizon. The bottom is a clear sky reflectance, and then as we keep increasing the cloud to red curve is an optical depth of 10, 0.1. The orange is optical depth of unity. The green is optical depth of 10, and the blue is an optical depth of 100. Now, optical depth is a parameter that's used to measure how much scattering stuff is there. An optical depth of 1 basically means if you laid the cloud droplets flat, together, 1 droplet thickness would be sufficient to block the whole, beam in there. That's considered an optical depth of 1. And but the particles in the atmosphere are randomly distributed, so an optical depth of 1 means that exponentially there's still about like 30% of the radiation would get through unscattered. And so this way, an optical depth of 100 would be like a cumulonimbus cloud, about as thick as they get. And so this again shows that the radiation is dependent on the cloud properties in there. On the right is the same thing. The left one of the cloud is up high, like a cirrus cloud at that level. On the right is a cloud near the surface, and it includes absorption by atmospheric gases. But so that way you see they're similar in there, except that everything's been kind of depressed because there's absorption going on by water vapor. Our next slide here, this is not exactly radiator transfer here, but this is what happens with the aerosols that are hygroscopic. At the top, we've put in with a about 5 different dry sizes of the aerosol. This is ammonium sulfate. And as the humidity increases, then they drift downward where you see the big round circles, and they pick up water. And in the process, they're changing the refractive index. And what's actually the color it shows is the efficiency of scattering. So that also changes as the humidity increases. And on the right is what's called this asymmetry parameter, which is the amount of forward scattering that the particle does. And so the arrows show actually kind of a hysteresis loop that's going on in there, because a dry particle, it doesn't respond to humidity until it reaches a certain high level where, of deliquescence, where it suddenly picks up water and then stays on that black curve. And then if the humidity decreases, then it reaches a point of crystallization where it dumps all the water that it has and becomes a dry particle. So that's a complicated behavior that aerosols have in terms of relative humidity. And we include that behavior when we're calculating climate. So this basically, again, shows more in schematic terms as the relative size of the aerosol as it increases when the relative humidity goes from 0 to like 100%. And the particles essentially become cloud droplets. And the mass fraction means that, water is basically becomes essentially water. So that's what changes the refractive index. On the right, it just shows that we can model their radiative effects of this type of relative humidity dependence. And here are some more curves of the Mie-Scattering parameters for sulfate mineral dust. The point of these are basically just to show that they depend on the composition, and they also depend on the size in there. So I don't think we want to dwell too much on these curves. There's more of this. This is, again, converting those Mie-Scattering results into the reflection and the transmission and the absorption at the bottom. And again, point here is that you see that it's all wavelength dependent, and we have to go and calculate all this stuff in detail to get their effects in the climate model. Another flipped.
Sorry, everybody. We tested this before and it flipped.
Now we're dealing here with thermal radiation. And for some of you who have taken some physics, I mean, you've probably heard the term like isothermal cavity, and then you have if you make pinholes in it, the radiation that comes out is the so-called Planck thermal radiation. And the point of this is that that isothermal cavity is in radiative equilibrium. And that's why that the radiation then, by kind of definition, is Planck radiation that comes out of the pinholes. That's Planck theory that dates back, 100 years or so. And on the right there, the point is that if you put in a kind of a slab of whatever scattering or absorbing material inside the cavity, and also have it be at the same isothermal temperature, then the radiation that comes out the pinholes is still going to be the Planck radiation, because everything that's in that pinhole or that in a isothermal cavity is in equilibrium. So all these processes of transmission, emission have to balance out in such a way that the Planck radiation comes out. And so this is the way how we can come up with the formula in the middle for the emissivity. Otherwise, it's like, how do we know how much something is supposed to emit in there? But this kind of helps us to, define the parts of the formulas that are used in, radiative transfer. The transmissivity is just exponential extinction, or so-called Beer's law, and then emissivity that comes out from this isothermal cavity consideration in there. And so there on the right is the full formula for the emission coming out as being a function of the emissivity is actually proportional to absorptivity, and then the other component is the transmitted part in here. So well, here we go again. So we use all that information to calculate what's called a line-by-line calculations of the radiation in the atmosphere in there. So there's absorption coefficients that are a function of wavelength, and so we can calculate this precisely at every wavelength, and then we have to do this for thousands of wavelengths, and then we could see what each gas does in the atmosphere. So what you see here is basically there's absorption by CO2 in the 15 micron region. Water vapor absorbs over the entire spectrum. And the way what we do is we calculate the radiation going up in the atmosphere, and then we calculate from the top going down. And then the difference between those two is what's called net radiation. And then when you difference the net radiation, then on the bottom right is what you wind up with is a cooling rate in there. So what happens, that shows is that the radiation is basically cooling the atmosphere. There's a lot of cooling going in the stratosphere, and much less so in the troposphere. And this is where we get into the fine detail of atmospheric radiation. In the middle of, this is for carbon dioxide, in the middle of the 15 micron band, the top left, you can see there's hundreds and thousands of individual absorption spectral lines in there. The top curve is for what happens in the stratosphere. In the stratosphere, there's much less air pressure, so there's the spectral lines are more distinct. And the bottom left is the same CO2 spectral region, but at the ground surface, where the broadening of the collisions with the air molecules is what broadens the spectral lines. So what's going on is that the strength of the line basically stays constant. It stays at the same wavelength, but it just gets spread out wider when the pressure is larger. And so in the line-by-line calculations, we did all this calculation basically going line by line by line. In the GCM or climate modeling, we can't afford to do that. So what we're doing here is reordering the spectrum by the order of the strength of the lines. So the middle part is exactly the same spectrum on the left. It's just been reshuffled. So the strongest absorption is, you find it on the right there. It's this log in the logarithmic K absorption in there, and same thing on the middle, on the bottom for the larger pressures. Now this still looks complicated in here. So on the right is what we call a cumulative frequency distribution. We add up the probability distribution from going from the weakest to strongest, so that the sum is basically unity. And then on the bottom left, or bottom right, is we kind of flip the axis from the Y to X. And so here's what you have is what's called the K distribution. And we've reordered the absorption coefficients. And so what we have is what you call maybe consider as a synthetic spectral line that includes all the absorption within that spectral interval, but it's been reordered according to the strength. The strongest absorption is on the far right and the weakest to the left. And the other smooth curves in there is it's a band model that has been fitted to that. And that's what we use to then manipulate this absorption at the top. This is a Malkmus model. It has analytic properties that you can do all this manipulation. And what we actually do is on the lower or the left is we fit the spectral line transmission to the band model transmission. So we fit the band model just needs two parameters to define it. And that's what we're doing in those two at the bottom, is refitting the band model, which is an approximation to the line-by-line data. And then given the band model, we have the ability to kind of slice and dice however we want with the absorber amount included. And on the bottom row to the right, we can chop it up into intervals that are, you only need like 5 calculations to do the same thing that you needed, 1,000 calculations for. and we can align these vertically, and so that's what's called a correlated K distribution that's correlated with height, and so we can do the entire atmosphere without you know, a much faster rate and still maintain the accuracy.
Sorry, everybody, for this.
Yeah, this is not cooperative computer.
Nope.
This is an example of how clouds, the cloud scattering, cloud effects are done in the climate model. The cloud is kind of, again, angle dependent. And so the curve that you see there is sort of what you'd be looking down from the space in there. So you see what's called limb darkening, meaning that the cloud would be the brightest or the most emission straight, you know, in the nadir direction, and toward the edges of, you know, the intensity would fall down. So the blue curve at the top is what the clear atmosphere looks like. And as you put in cloud, that decreases the amount of radiation going out. And so it's, again, an optical depth of 0.1. That's like a cirrus cloud is the red curve. And then optical depth of 1, that's kind of, again, a thin cloud. And at the bottom is an optical depth of 10. So the internal radiation, the cloud gets more saturated, but it has a strong influence on how much radiation gets out, goes out the atmosphere. So this is part that gives you the greenhouse effect that clouds have. And on the right is just an indicator that you know, we have to do this angle dependence for the emission, otherwise we make an error of 3 or 4 watts. And here's an additional aspect of clouds, in that there's clouds do a little bit of scattering in the thermal. Mostly they're just absorbing. And on the left is the cloud cover, so roughly about 50%. And the bottom left is a cirrus cloud, high cloud cover. And on the right is this thermal scattering effect of the clouds. It scatters the radiation, and in the process kind of keeps the radiation from being emitted out to space, so it acts as a further to strengthen the greenhouse effect. And it also increases the radiation going into the ground on the lower left. The effect is kind of small. It's only about 1.5 watts for the outgoing flux and about half a watt for the downwelling flux. Now I think we're getting close to the end here. This is polarization. The light is actually electromagnetic radiation that is kind of transversing. It has polarized in there. For most of the things in climate, we treat it as just scalar scattering. But polarization is something that is important in remote sensing. And this, again, plot shows that basically left from it's a function of refractive index and size. And it's calculated by the Mie-Scattering. And what you see on the left are kind of smaller aerosols, and with a refractive index indicating they're large, like 1.5 or so. In the middle is 1.4, and on the bottom is 1.3, which is water. And so you see the shape as a function of the scattering angle. That means that we have to look at the angle that the light gets scattered by this particle, and you see the shape is changing. So we can think of this as kind of an angle spectrum that identifies a particle size and a refractive index, or in effect the composition of what's scattering. And it's unique for the given refractive index and a given particle size. So that's how we can tell aerosols apart from clouds in a mixture of where you have clouds and aerosols coming in. So this is important remote sensing, where you're looking down and you see, the photon that your detector might detect may come from the aerosol. It could come from the ground surface, or it could be cloud contaminations that's within the pixel. And the instrument can't tell the difference. And that's what makes remote sensing difficult. But if you include polarization to have a polarimeter do this analysis, This gives you kind of an extra handle to look at this, so you can separate out contributions that would be due to an aerosol and to the cloud or to the ground surface. The ground surface would be basically a flat, very little reflection in the polarized light in here. So that's, this last slide shows a kind of example where vegetation and bare soil on the top left are measured in intensity, and there's significant difference. On the right is the same kind of vegetation measured in polarization, and they're very clumped, but you notice that the scale is several orders of magnitude smaller. So this is just again showing that the surface is has a very different polarimetric characteristic than the clouds and aerosols. And if you have all that in a measurement and the intensity and polarization, you can subtract out the soil component and just have the aerosol and cloud particles that you can then separate out directly. So I think I'll stop here and entertain any questions that people might have.
Perfect. Thank you again, Andy. And thank you everyone for bearing with us with the image issues we had with this one. We're going to turn it to David for the first question to start off the Q&A period. But again, please use the chat function for any questions that you have for Andy.
Andy, thank you very much for this comprehensive, complex look at what goes into building an atmospheric radiation scheme for GCMs. For those of you who thought that the calculation of what greenhouse gases are going to do to the climate was based on back of the envelope calculations, I hope you're properly chastised. So the question I have, Andy, is where do you see atmospheric radiation calculations for a GCM going in the future? Assume that there's a big increase in computer capability. Where are the areas that will be able to be improved in the foreseeable future?
Well, okay, that's kind of an open-ended question.
Yes.
There are several different areas. One area is that what are the climate GCMs able to predict, specifically in terms of clouds? If you look up at the clouds, you see all kinds of clouds. They're flat and angular and small, big and thick and whatever in there. Climate models have a hard time to predict the clouds based on what you call first principles. It's very complicated. And so there's a lot of empirical improvements being made in predicting what kind of clouds the model can generate. And for also in a climate model, we're not really making point calculations. It's done in terms of grid boxes, which are maybe 100 miles across or so in there. So there's a lot of different things that can go in there. So we can have a lot of complicated clouds in there. So in terms of the radiation calculations, the only thing that we can really handle analytically or mathematically is what's called plane parallel homogeneous clouds. That we can do in a lot of detail in there, but that's not what the real clouds are. And the model clouds are also sort of in between. They have fraction grid box that have clouds and are overlapping clouds in there. And how to handle all that in a model is a challenge in there. Besides that, there are also the details of how big are the cloud particle sizes, what is the size distribution, ice particles. Ice particles come in all different kind of shapes. They may be flat plates, they may be rosettes. I think models are starting to maybe make some predictions on that basis, because that depends on a lot of how much what the humidity is, the updraft velocities and temperatures, all that kind of stuff comes into that. So those are some of the parts of things. There are some parts, I mean, there's always increase in detail for the absorption lines that are also there continuously being upgraded and with observations and modeling in there. But those I think are something that with, again, increased computer time, we can model with reasonable accuracy in there. So the other aspect, I think, of the climate radiation is making calculations in such a way or retaining information at spectral intervals, which then can be used for comparison to observations, like cloud observations, temperatures, water vapor distributions, and so on, to see if that's what the model is calculating is actually something that you can compare directly to observations. So there are lots of different areas that we can have to work on. So it's not like we can say the problem has been solved.
Thank you.
Great. Thank you so much, Andy. I have been monitoring the chat. I don't see any other questions right now for Andy, but I will share my email in the chat. And if you have any questions for either of our speakers from today, feel free to email me. Oh, we just got a question in. So John says, from the It's a Complex System file, some climate modelers spend some time and effort trying to understand and model the contribution of evapotranspiration by assessing the stomatal resistance of leaves. I think that's more of a comment than a question about.
For Randy.
And it's a question for Randy from previously. So we'll be sure to share any other questions or comments you have.
I might comment on that again in more general terms in there. The climate models are becoming more, I guess you might say, complete, in that originally all clouds, vegetation, everything was prescribed in some sense. Ozone distribution. Now they're actually being calculated. So the vegetation is now interactive with the climate model, so that vegetation is being computed. So that's where all the leaf index, evapotranspiration, that becomes a more kind of a issue that we can include in the model. Radiation going into the ocean, what the hydrosols are doing, phytoplankton, how does that interact with the radiation? Heretofore, all of that was kind of a prescribed boundary condition, but now is becoming more part of the model. And also, all along, like carbon dioxide has been kind of a force. It's a boundary condition just put in. Now the climate model is running a carbon cycle. We want to know where the carbon sinks and sources in there. So the climate models are becoming more realistic in terms of all the physical processes that contribute to climate and how they interact. So that way we can then have a better handle as to what's going to happen in the future, because we have these different processes also being interactive. So for CO2, for example, CO2 feedback is a key question that I think we should be worried about. As the climate warms, the polar regions warm faster, and we have carbon dioxide and methane being emitted from the permafrost, and that becomes part of the climate forcing. And so all of those things are what we're starting to include more and more in the climate model. So they're not, they're indirectly part of the radiation, but they're not strictly just a radiation question.
Thanks. Well, that concludes our presentations for the day. All of the lectures from today and from past in the series are recorded and can be found online at the ccrun.org website. I just provided a direct link to it in the chat. These from today will be uploaded within the next week, so you can go and listen to them on your own time in the future, or if you want to share them with anybody. Our next and final webinar in the series is going to be taking place next month on July 16th at 3 p.m. We'll be sending out a link to register for that webinar in the coming weeks. And I just wanted to thank everybody. Thanks to both Randy and Andy today, and to David for making today happen.
And to Danielle.
Thank you. Thanks, everybody. Have a great afternoon.
Thank you. That was great.
All right.